started on my laptop screen, ready for the Python scene. All those lines of text so clean, let's code and chase that dream. Python world, here we go. Write the script, let it flow.
In this video, we're going to explore computer programs and algorithms. The goal today is not to get into programming just yet, but to go over some common definitions, terms, and background that we're going to need to be successful Python programmers. Let's get started by talking about computer programs and code. The main goal of programming is creating or modifying computer programs. In simple terms, a computer program tells a computer the sequence of steps it needs to do to complete a specific task. For example, if we wanted to write a program that calculates the average grade on a test, we would need to tell the computer each step needed to calculate that average and then output it to the user. While the steps required to take an average may seem very straightforward if you explain them to another person, computers tend to be very literal and specific. We cannot simply say add all the grades together. Rather, we'd have to tell it how to do that in detail, such as input the first grade from the user, add it to the total. Input the second grade from the user, add it to the total. Input the third grade from the user, add it to the total, and so on. This means even simple programs can be comprised of a very large number of simple instructions. These instructions are typically executed one at a time, one after the other, in a predefined order. And these instructions tend to fall into three basic types. The first is input, where the computer receives data from a source outside the program, such as the keyboard, file, network, touchscreen, webcam, or so on. The next type of instructions are process instructions. These are where some calculation or computation on data is performed. An example might be arithmetic, memory management, string manipulation, and many other possibilities. And the last instruction type is output, where the computer places the data it's processed somewhere outside of the program, such as on the screen, in a file, transmitted over a network, or so on. These instructions in a computer program are understood by the computer as machine instructions, very low-level and simple instructions your computer's processor can understand. They tend to be very hardware-specific instructions, involving moving or manipulating data stored in your CPU's memory called registers. For example, it might be something like retrieve the value stored at location X, add 12 to it, and store it in memory location Y, where X and Y would be specific memory addresses. Another example might be an instruction that states memory location X contains an odd number, start executing the instruction stored in memory location Z. The point is, these are very literal, low-level, and very specific instructions to the computer that might not be the most accessible for us as humans to understand. Here's an example of what these instructions might look like in a computer's memory. As you can likely tell, this is rather difficult for a human to understand, and would require memorizing a large number of hexadecimal codes. To make this a bit easier to work with, assembly language is often used to represent machine code in a more human way. Well, a little bit more human. I'd still struggle to tell you what the specific program that we're showing right now is doing. Assembly also tends to be fairly hardware specific. What works on one CPU, like an Intel processor, and operating system like Windows, might not work on another operating system like Linux, and a different CPU architecture like the ARM architecture. Because this is so hard to understand at this low level, as well as it not being very portable, in most cases today, most programmers use high-level programming languages. These are languages such as Python, Java, C, C++, PHP, and many others. High-level programming languages aim to hide many of these low-level hardware details and provide a more natural language-based format that's easier to manage, easier to understand, and makes development faster. Abstracting these low-level details also allows our programs to be more portable, meaning that they will work on different kinds of hardware and operating systems, and allows for us to concentrate on more important details like the logic of our programs rather than how it's working on a certain operating system or how the memory is being managed. As a simple example, let's take a look at this Python program that asks the user for two numbers and then outputs the result to the screen. Even if you don't know anything about Python yet, you'll probably have at least a general idea of what these lines of code do. We'll get into the specifics in coming weeks and lessons, but you can probably tell the first two lines have something to do with taking input from the user, from the input keyword, and the last line has something to do with outputting it from the print keyword. When we have the instructions of a program like this, we call it source code, or sometimes just code. When we call a program open source, it means we have access to the source code. When the program is closed source, it means we only have access to the machine code to run the program. We can't modify it easily. So let's say someone gives us the source code for their computer program. How do we actually use that source code? Well, there's typically one of two ways computers can use source code. They can either compile it to another form, or they can interpret it live. When we're using a compiler, before we can execute or run our program, we first need to compile it into machine code or another intermediate form, such as bytecode. And this is done using a program called a compiler that's processing the source code, linking in any needed libraries, and then finally creating an executable file that's specific to your hardware and operating system. One example would be an exe file on Windows. This executable file then can be run in your native operating system. The other way we can use source code is by interpreting it. When using an interpreter, the source code is executed one line at a time, and the machine code instructions are sent directly to the processor, rather than creating some sort of intermediate form. And this is given to you as output lines, live as the program is running. So there are trade-offs between these two approaches. Interpreted programs tend to be slower and require more effort from the user to run. They also require the source code to be shared. The advantage is that they tend to be more portable, as they're not compiled for a specific hardware or operating system. Compiled programs, on the other hand, tend to be faster, easier to use for end users, and they don't require the source code to be shared. So that raises the question, is Python, the language we'll be using for this course, interpreted or compiled? Well, this depends on the implementation of Python you're using. Interpreted or compiled is really more of a characteristic of the implementation of the language rather than the language itself. For this course, we're going to be using an implementation of Python called CPython. This is the standard implementation of Python, which is a bit of a hybrid approach. CPython first compiles the Python source code into bytecode, which is an intermediate form. And then that bytecode is interpreted by the Python virtual machine. From the user's perspective, this might look like it's being interpreted as the bytecode is immediately executed. However, it still retains many of the advantages of compiled programs. Don't worry if that sounds a bit confusing right now. The main takeaway for now is that this high-level source code that's easy to understand by humans is compiled into a form the computer can understand. That's easier to understand by computers. And then those instructions are carried out by the computer one at a time in a sequential order. So at this point, you may be asking, is this all computer science is? Is computer science just about creating programs and running programs? Well, that's a bit like asking if the visual arts are just about paintbrushes, or if engineering is just about wearing a hard hat and measuring things. Computer programs and programming are one of the many tools computer scientists use. And it's the way we implement our ideas, but the main focus of computer science is one of computation. It's on computation, information theory, and specifically algorithms. But that may raise the question, what are algorithms if not computer code? And how are algorithms different from computer programs or source code? Well, let's get into that now. As we've already covered, computer programs and source code are step-by-step instructions written in a format that a computer can understand and execute. This means that source code has to follow strict and specific syntax and grammar that's defined by the programming language. On the other hand, while algorithms are also step-by-step instructions, they're not necessarily in a predefined syntax or in an understandable form that a computer can use. Rather, they're intended as means of communicating an idea between human people, and as such are often expressed in a natural language or pseudocode that has no set syntax or grammar. Source code might look something like this. This is an example of a Python program that counts the number of students in a lecture hall by pointing at each one, saying their name, and then adding 1 to the total. Whereas an algorithm is written in pseudocode might look something like this. Pseudocode is not a formal programming language, but an informal description of an algorithm intended only for communicating algorithms to other people. We can also represent algorithms visually using things like flowcharts, like this one. Again, this is as a means to communicate an algorithm to other people. It's not something a computer can understand. We can see source code and programming as a way of implementing an algorithm and turning it into something a computer can understand, whereas algorithms are general procedures to compute the solution to some problem. So to summarize, source code is something written in a specific programming language that has to follow a specific set of syntax and grammar rules. It's meant for a computer to understand and be able to either turn that into an executable or to run it directly. Algorithms are an informal description of a solution to some problem that another human can understand. They're not necessarily tied to a specific programming language and not necessarily something a computer can understand. So if there's no rules or grammar or syntax for algorithms, what rules do algorithms have to follow? Well, there are 3 properties an algorithm should satisfy. The first is an algorithm should remain unambiguous, meaning that no assumptions are needed to execute the instructions in an algorithm. This also means that each instruction has to be precise, and there can only be one interpretation for how this instruction will be carried out. The next rule is that it has to be executable. No instruction in the algorithm should be impossible, and it should be possible to carry out the algorithm in practice. There shouldn't be nothing that we can't actually do. Lastly, the algorithm has to eventually terminate, meaning there has to be an end or some way for the algorithm to eventually stop. This is sometimes referred to as halting. Let's now take a look at a somewhat silly example, and that is an algorithm to make a peanut butter and jelly sandwich. Recipes such as this are also a form of algorithm. They have an ordered set of steps. The steps should be unambiguous so the reader can follow along, and the steps must be possible to complete. And there should be a point in which the recipe is eventually done and your food is ready so you can eat it. Here I have 2 different algorithms for creating a peanut butter and jelly sandwich. In theory, both algorithms accomplish the same thing, but are they both good algorithms? Are they both equivalent? Does either one satisfy our requirements? Think back to the properties of a good algorithm I just covered, and try to evaluate these 2 algorithms. I'll give you a moment to read both over. Feel free to pause it if you need more time, and unpause it once you think you have a decision.
Flying lines in haste, got to run, no time to waste. Syntax green lights turning bright, Python dreams in late night light. Loops and flows, recursive call. See it now, we'll break the wall. Data points, they twist and blow. Fast forward, run, let's watch it grow. Python tapes rewind the mind. Bits and bytes, they all align. Screen is flicker, lines unwind. Fast forward code, let's hit rewind. Leads the way. In this loop we code all day. bits and bytes, they all align. Screen is flicked.
And we're back. But instead of me just giving you the answer, let's actually put these algorithms to the test and see how they perform. We're going to test out those algorithms to make a peanut butter and jelly sandwich. But before we get started, there's a few things we need. Since we're making a peanut butter and jelly sandwich, we need some peanut butter. And we're going to need some jelly, of course. And we're going to need some bread. And we'll also need a plate to put our sandwich on. And maybe a knife and a spoon, just in case they come up. Now, the two algorithms we had are fairly simple and straightforward, but algorithm 1 was even more simple. It was only 4 steps, and one of those was to eat the sandwich. So we're going to go through each one of those steps, and I'm going to pretend that I'm a very literal computer and do exactly what the steps say, sort of like what the computer would do when you're programming. One of the things to get from this lesson is that computers are very literal, and they will do exactly what you say, even if that makes no sense or causes an error. So algorithm 1, the first step is put peanut butter on bread. We've got our peanut butter, we got our bread. Let's put the peanut butter on the bread. Okay, accomplished. Step 2, put jelly on bread. Jelly, bread. Great. Now we want to put the other half of the bread on top. Well, we can give that a try. Oh. And then eat. Delicious. So we can see that there was a few problems with that algorithm. It was not specific enough, and many of the steps were ambiguous. So they could be interpreted different ways, like this silly one. So with what we have remaining of our bread, let's try algorithm number 2. So the first step in algorithm number 2 is place 2 pieces of bread on the plate. But even that is a little bit vague. I mean, we have some bread, but how are we going to get it out? It just says put them on the plate. So maybe we just rip it open. And here's a piece of bread. There's a piece of bread. They're on the plate. Good. So step number 2. Put a knife in the peanut butter jar and scoop out some peanut butter. Here's our peanut butter. Doesn't say anything about opening it. So that doesn't work. So that's going to cause a problem because that's an impossible step. Maybe we'll give them the benefit of the doubt and open it up. But even then, there might be a few things we didn't expect. And this is something that can happen in real programming. Sometimes you'll encounter things that you don't expect. In this case, we have a seal that maybe we didn't think would happen. Maybe it's user input that we don't expect. And later in the course, we will talk all about exceptions and how to deal with those. But for now, since we didn't deal with it, we just go right through. Good. We got the knife in the jar of peanut butter. Now spread peanut butter on the piece of bread is the next step. So we have a piece of bread, we've got our peanut butter, we'll spread that on there. Okay, so the next step, put spoon in jelly and scoop out some jelly. So we'll give a benefit of doubt and actually open it this time. So put spoon in jelly and scoop out some jelly. There we go. And then the next step is spread jelly on a different piece of bread. Okay, we got a different piece of bread. We're going to spread that on. Good. And then place 2 pieces of bread with the jelly and the peanut butter together. The problem is before we didn't quite spread it right. So we don't really have one, and that makes that step impossible. But again, we can give the benefit of the doubt, and we could take some peanut butter out here. So we have a piece that actually has peanut butter on it. And now that step 6 says place the 2 pieces of bread with the jelly and the peanut butter together. So we have a piece with jelly, a piece with peanut butter, and we're going to put them together. There we go. Again, it wasn't specific enough. And eat. Delicious. So again, the point to stress here is we need to be very specific in our instructions. So if we actually wanted to make this algorithm in a way that works, we would have to be extremely specific. So there is no chance that it could be interpreted in any other way. We'd have to say how we're opening the jar. We would even have to say we're checking for a seal, removing the seal, putting the knife in with the sharp side facing down, scooping it and putting it on a specific piece of bread, and clearly specifying that when we put the bread together, we do it with the jelly side and the peanut butter side touching, not the other way around, which can be quite messy. So I'm going to get cleaned up and we'll go back to the slides. What you should do is take a few seconds to think about how would you write this algorithm in a way that would be less ambiguous. Okay, that was fun and quite a bit messy, but what did we learn from it? Well, hopefully the main takeaway was that algorithms need to be as precise as possible. And this is even more true when we start implementing our algorithms as code. Computers lack the ability to make assumptions and fill in the blanks left in our algorithms or our code. When you start getting out there and programming, you're quickly going to see that computers can be quite literal, and they're going to do exactly as you ask, even if that means running a loop forever and never stopping, deleting all your files, or even trying to add the words one and one together rather than the numbers one and one. It will be important to keep this in mind as we move forward in the course and start programming for ourselves. Most algorithms we are going to encounter can be broken into 3 simple types of instructions or structures. These are sequences, selections, and loops. A sequence is a series of actions in a specific and set order. Each action is carried out in order, one after another. Action 1, then action 2, then action 3, and so on. In our peanut butter and jelly example, the algorithm was sequential. First, we open the peanut butter jar, then we put the knife in the peanut butter, and so on. Each step occurs after the last one in order. Selections, on the other hand, allow us to ask questions and determine the next step based on the answer. These questions always have a true or false answer, and a different path is taken based on if the question is evaluated as being true or if it's evaluated as being false. In programming, the most common selection is the if statement, and you'll probably see this a lot in your Python code. Let's take a look at another example. Say we want to create an algorithm to look up someone's address and phone number in a phone book. For those of you that don't know, a phone book is a dictionary of sorts of people that allows you to look up their address and phone number by their last name. These tended to be a lot more popular back in the day before cell phones allowed you to just store everyone's name and number you needed. Back then, everyone in the town or township would have their name listed in a phone book, alphabetically by last name, and it would allow you to look up their address or phone number. These days, they're kind of irrelevant and they don't really send them out anymore, and they tend to be just limited to landlines. So the way this works is each page in here has a listing of last names, sometimes some first initials, and then beside it an address and a phone number. Each one's listed alphabetically by last name. So how might we make an algorithm to look up someone's phone number and address from a phone book like that? Well, part of the algorithm might use a selection statement like this. We open a page in the book, search it, and ask, does this page contain the name we're looking for? If the answer is yes, we return that phone number. If the answer is no, we might move on to the next page and keep looking. The last construct we'll see are loops. Loops allow us to repeat certain steps over and over again until some condition is met. This is extremely important if we need to do the same action many times, or if we don't know how many times we need to do a step beforehand. As an example, let's say we want to count the number of students in a lecture hall, but we don't know how many students are in that lecture hall beforehand. So we're going to have to loop through and count each one at a time. Sort of like if you're pointing to each student and saying 1, 2, 3, 4, and so on. Each new student would be a reiteration of that loop. So we might start by counting the first student, but then we need to check if there are more students to count. If there are more students, we need to loop back to that first step and count that next student. This sort of loop keeps going until there are no more students to count, and then the answer to the question, no more students to count, is true, and we can finally exit the loop and return the number of students. By combining sequences, loops, and selections, we can create quite complex and interesting algorithms. For example, the algorithm depicted here in this flowchart will check if a given number is prime. So that's quite a complex concept that we can solve by binding sequences, loops, and selections. And almost all the programs we'll be creating in this course are going to be some set of sequences, loops, and selections in a specific order. So now that we know a little bit about algorithms, how do we evaluate them? How can we tell if an algorithm is good or better than another algorithm that accomplishes the same task? Well, if two algorithms have the same inputs, and they have the same outputs, and the results are the same, are they equivalent regardless of the steps used? Or is there more to designing algorithms? And the answer is yes. There are other factors than simply returning the correct solution. And let's explore this with that phone book example again, and take a look at two different algorithms that accomplish the same thing.
Okay, so the problem we're facing is given a phone book like this, which is a directory of people listed alphabetically, starting with last names with A at the beginning, and going all the way to last names with Z at the end. How do we find a specific person's phone number and address? So for each listing in this phone book, we do have a last name, some initials for the first name, an address, then a phone number. And we're going to assume our algorithm has a copy of this phone book, as well as the name. Those are the inputs to the algorithm. And what our algorithm should do is return the phone number of the person we gave it a name for. And we're going to assume, for the sake of this example, that they are listed in the phone book, which isn't a realistic assumption. Not everyone's in this phone book. It's mostly just landlines. But we'll assume that that's true. So there's a few different approaches we could take to finding that. The most naive approach would be to start at the beginning in the A's and look, is the person here? Maybe we're searching for me, Daniel Servos. So am I in the A's? No. So go to the next page. Keep looking for the A's. Am I on this page? No. Go to the next page. On this page? No. Go to the next page. We'd have to keep going, until we eventually got somewhere in the S's where we found Servos, D, and then we could return my name. Now the problem with that approach is we would have to go through every single page until we find the name. So if your name's like Alfred Advark, that might not be a big issue. You're probably going to be on the first few pages. But if you're like Zachary Zebra, then you're going to be at the last page and you have to look through every single page of this phone book. So that algorithm works, but it might not be the most efficient. So we can take advantage of the fact that this phone book is sorted alphabetically to make a much better algorithm that's faster and more efficient. And what we do is, instead of starting at the beginning with A's and keep going until we find it, let's cut about halfway through. Let's say maybe we end up somewhere in the M's. So on one side, we'd have the alphabet heading towards A. On the other half, we're going to have the alphabet heading towards Z. Now, we are smart, so we know that Servos, the name we're looking for, starts with an S, and that means it's going to be in the later half of the alphabet. So that means we don't even need this first half of this phone book. So we could just like that and chuck away the half we don't need. We only need the half that's likely to contain the name. And now instead of keep going page by page, we do the same thing again. We do a cut. We take a look. Oh, we can see maybe there's an R on this side, S on that side. We cut again, throw out the half we don't need, and then we take another cut in the half. Look halfway through. We see, oh, we're in the S's now. Oh, maybe this side has Servos. So we cut again, throw that away. And we keep doing this, cutting in half, looking. Oh, it's in this side, so we throw that away. Cut again. Oh, it's on this side. So we start looking, and if this is our only page left, we know it's here, and then we return the name. So the idea with this second approach is we're not going page by page, we're cutting in half, and we look at both halves, we see, oh, we know it's going to be in this half, and we cut in half and keep on going. And this is taking advantage of the fact that the book is already sorted alphabetically. This sort of approach won't work if the names were random. So let's head back to the slides and compare these two algorithms in a little bit more detail.
And we're back. The first algorithm we looked at simply checks every page in order from the start to the end until it finds the name we're looking for and then returns the result. This would be an example of a linear search algorithm. I have a flowchart that sort of depicts this algorithm here, and it should eventually return the correct result as long as we assume that the name is in the phone book. The second algorithm we looked at was a form of binary search, where we took advantage of the book being alphabetically ordered and started halfway through the book, throwing away the half we know did not contain the name each time. Again, this algorithm will return the correct result, assuming the name is in the phone book and the phone book is in alphabetical order. So how do we know which algorithm is better? which one might we want to actually implement in our code if we're creating a computer program that has to do this? Well, the first criteria we can use is correctness, which simply means, does this algorithm return the correct result for all possible inputs? And also, will it eventually terminate and give us a result for all possible inputs? Both algorithms in this case are correct, as long as our assumptions are true, that the name actually is in the phone book, and as well for the binary search, that the phone book is in alphabetical order. If our phone book was in an unordered order, then binary search would be incorrect, because it wouldn't be able to do that approach of cutting through and then being sure it was in the other half. However, as phone books are sorted, we could use either algorithm and still get the correct result. So how do we know which one is a better algorithm? Another factor we need to consider is the speed of the algorithm. Which algorithm is faster? And we could evaluate this in a few ways. One approach might be trying to implement both algorithms and then timing with a stopwatch or something, which algorithm is faster for a few given inputs. However, there's a few problems with this approach. First, there could be different hardwares at play here. For example, one computer might run faster than the other due to hardware differences rather than differences in our programs. Or maybe even using the same hardware, we could get different results due to different background processes or other factors with the computer at the time. A second issue would be, what inputs do we use? If the name was on the very first page, such as like Alice Advark, then linear search should have a significant advantage. But if we were doing something like looking for Zachary Zebra, then it would be at a significant disadvantage, just based on what inputs we give it. The way we deal with this is to use something called time complexity, rather than trying to measure the performance in terms of seconds. Time complexity is a representation of how many basic steps or operations are required to be performed by an algorithm to return a result and terminate. In our example, a basic step might be turning a page in the phone book or comparing a name with another one that we're looking for. This measurement is always relative to the input size, and this is typically represented by the variable n, and should be true regardless of the number of pages or names we input to the algorithm. We also normally look at the worst possible case for the algorithm. So in the case of linear search, we'd want to know how many steps would be needed if the name occurred on the last page rather than some other page in the phone book. For linear search, the worst case is that we would need to turn the page n times, where n is the number of pages. This would mean the name occurs on the last page of the phone book. For binary search, we need log n plus 1 page turns to reach the name in the worst case. We represent these worst cases in a mathematical notation called big O notation. We won't go into big O notation or time complexity in this course, and we won't be asking you to calculate it. But know that big O notation gives us a way to classify algorithms according to how their runtime grows as a function of their input size. This gives us a few different classes of algorithms in terms of performance and allows us to compare different algorithms. In this case, linear search, as the name would imply, has linear performance, where binary search has logarithmic performance. In general terms, this means the binary search algorithm would be faster in the worst possible case. Again, we won't be going into time complexity or big O notation in this course. For now, just know that we can use them to evaluate the performance of our algorithms, and not all algorithms are equivalent, even if they return the same correct results. And with that, we're at the end of the lecture. Hopefully you learned a little bit about computer programs and algorithms today, and now you can move on to our other lectures and readings on Python programming. Thank you for watching, and have a great day.